so today we're going to talk about electrochemistry. So electrochemistry is the study of the interchange of chemical and electrical energy. There are two processes involved in this that we've discussed before, oxidation and reduction. First, you have the generation of an electrical current from a spontaneous chemical reaction, and then we use that current to produce a chemical change. So, as a review, oxidation reduction, remember, involves the transfer of electrons from a reducing agent to the oxidizing agent. Remember, the reducing agent is what is oxidizing, and the oxidizing agent is what is reducing. Okay? So, again, oxidation refers to a loss of electrons, and reduction is a gain of electrons. Again, if you need more review on oxidation reduction, you can review that in your textbook. Section 4.10 would be good review for the exam as well. So, in terms of a galvanic cell, that is a device in which a chemical energy is converted to electrical energy. The oxidizing and reducing agents have to be physically separated so that the reaction energy can be used. And we do this in this fashion. So on one side we have one half of the cell, right, where we have our oxidation occurring at the anode, and on the other half of the cell is our cathode, which is where reduction occurs. Okay, and if you think about this, is how batteries work. Okay, so you know batteries have a positive and a negative end, right? And that's how this works out. So they have to be separated. So in this instance, you have a zinc electrode in a solution of zinc sulfate, right? And then you have your other cell is your copper electrode with your copper 2 sulfate solution. And what happens is, when it's a spontaneous reaction, the electrons will leave the zinc solid electrode and travel through the wire. We can measure that through the voltmeter here. And then it enters the other electrode on the other side, and then that produces more copper ions. Okay, so our sulfate ions and our zinc ions will flow back and forth here so that we can maintain a charge. Our charge can be maintained, so we never have too much charge on one side or the other. And they flow through what's called the salt bridge. This is how we keep the two halves separated. So again, the cathode is where a reduction occurs, and then the anode, as I said a moment ago, is where oxidation occurs. And a good way to remember that is A and oxidation are both vowels, cathode and reduction are both consonants, to help you remember how that works. Okay, and again, this is because we're losing electrons at the anode, and then the cathode is receiving the electrons. Alright, again, that salt bridge that we talked about is just a porous disc that allows the exchange of the ions to keep things electrically neutral. Right? So because electrons are flowing to one side, you have to have some positive ions that flow that way, right, as well. So our electrons are flowing this way, which is why our zinc ions have to flow in that same direction, and then the sulfate ions will flow in the opposite direction, right? Because this side is losing negative charges, so the sulfate ion provides more negative charge here, right? And then we are losing negatives here, and then gaining them with those electrons coming in here. Alright, so that's the cell and what it looks like. Next, we're going to talk about the reactions a little more in detail. So, in this problem here, we want to identify the species in which the would receive electrons from the cathode and which would lose electrons at the anode. In other words, what's oxidizing and what's reducing. So, if we look at this, our first step is to break this up into two half reactions. Alright, so we have our magnesium going to a magnesium plus 2. And there's an arrow missing there in our notes. Okay, and then the other half is your hydrogen becoming hydrogen gas. Alright, so which side do our electrons need to go on here so that both sides are equal? Right, so we would have to have 2 electrons over here. So that -2 and +2 are 0. Over here we have +2 and 0 on the other side, so we'd have 2 electrons on this side. Alright, and that helps us decide which one's oxidizing and which one's reducing. Because remember, oxidation is a loss of electrons, right? So if we're losing our electrons, our oxidation number is increasing, right? So in this instance, what has oxidized is magnesium. And what has reduced is the hydrogen. Okay? We must always have something oxidized and something reduced. Okay? And so since this is oxidation, this will be at the anode, and this will be at the cathode, since it's reduction. We can measure this exchange of electrons, flow of electrons, by what we call cell potential. Alright, so the oxidizing agent pulls electrons through a wire from the reducing agent to the other compartment. Those electrons, of course, as I said a moment ago, flow from the anode to the cathode. This pulling electrons is what we call the EMF, or the electromotive force. Again, electromotive force for EMF. We measure the cell potential in a unit called volts. By definition, a volt is 1 joule per coulomb. Right? A potentiometer is powered from an external source in the opposite direction of the cell potential, and that can help us to measure that potential. The voltage is adjusted so there's no current that flows in the cell, so that the cell potential is equal in magnitude and opposite in sign. And so that's how the different cell potentials have been determined. And they're all based on a standard. And the standard which was used is the hydrogen electrode. So it's determined to set hydrogen electrode equal to 0 voltage, and at the conditions of 298, 1 atm, and 1 molar concentration. And then they compared all the others to that one, and then they could determine what each half reaction cell potential is. And so we have a chart of these standard reduction potentials, which can be found on page 843 of your textbook. Now these are all written as reductions, and remember we have a reduction and we have an oxidation. So to account for that, right, the one that oxidizes, right, when you look that up in the chart, you have to change the sign. Okay, the one that oxidizes, you have to change the sign because they're all written as reductions. And so if we reverse it, the reaction to be oxidation, we just flip the sign. Alright, so galvanic cells require that our cell potential be positive. Okay, one of the reduction potentials, again, has to be reversed, as we were just talking about. And when it is reversed, after we reverse it, then we add them together, and we have to come out with a positive answer, right? Greater than 0 means it has to be a positive cell potential. Again, when we reverse a reaction, right, the E for that reaction gets the opposite sign. Okay. If we multiply the reaction by a coefficient while we balance, E in this case is not changed, so that is something that's different. We've done these kinds of manipulations before, but the coefficient multiplying that does not change the cell potential. Alright, so let's look at a problem. This is the example problem on page 844 in your textbook. So we have the reaction of iron plus 3 and copper. Right? We determine our two half reactions. We have our iron plus 3 going to the iron plus 2, and our copper and are going to copper. So again, these are our two half reactions that I located on that chart in your textbook. And then I found their cell potentials, here, again, from the chart in their textbook. Okay. Now, one of these two reactions has to be reversed, right? So which one is that? So that's the one that's oxidized. So if we see here, we go from an iron plus 3 to an iron plus 2. So its oxidation number decreased, so this one is reduced, which means this one is oxidized. And so since it's oxidizing, we have to reverse it so that it will match what it looks like in the reaction above. So we end up with our iron plus 3 and 1 electron, and our iron plus 2. And so our cell potential is 0.77 volts for that. That should be E's. And then our second half we flip, so we have our copper solid going to copper plus 2 and 2 electrons. And that cell potential, since we flipped it, becomes negative 0.34 volts. Okay. Of course, just like when we did the redox reactions before, our electrons have to balance out. So since there's only one electron up here, we multiply all of these by 2 so that our electrons can cancel. Okay. And then we add them together. Right? So then we add our two half reactions together to get our final reaction. So we get our iron plus 3 and our copper going to our iron plus 2 and our copper plus 2. And then our cell potential is just the sum of these two values. Alright, so we just add those two together. Right? And we get 0.43 volts. Okay. Alright, so moving on, let's look at another example. In this one, we have aluminum and magnesium. Alright, so first we want to determine our half reactions. In one half, we have our aluminum, which is going to aluminum ion going to aluminum solid. Right. Again, we're missing our arrow here. So at one half reaction, and our other half reaction is the magnesium to the magnesium plus 2. Right? So, again, when we look at our chart, again on page 843 of our textbook, we can look up the cell potentials for these. Right? But one of them is reducing, and one of them is oxidizing. So aluminum goes from 3 to a 0, so that's reducing. And magnesium is going from a 0 to a 2, so that's oxidizing. So when we look up the reduction potential, we have to change the sign of the one that oxidizes. Alright? So, the one that we're going to, we had to reverse, of course, right, from the textbook, is the magnesium. So we have our aluminum plus 3 electrons goes to aluminum solid. And then we have our magnesium going to our magnesium plus 2 and our 2 electrons. We look up these cell potentials for these on page 843, and we find that aluminum is negative 1.66 volts, and then the magnesium in the table is negative 2.73, but we're going to make it positive since we reverse the reaction. Okay? So we can get the overall reaction by just adding these two together. Again, our electrons have to equal out, so we're going to multiply this guy here by 2 and this guy down here by 3. So we get 2Al plus 3 magnesium going to 2 aluminum plus 3 magnesium plus 2, because our electrons would cancel when we do that. And then determine the cell potential is simply to add those two together. 1.66 plus 2.37, right? And that gives us a positive 0.71 volts. Right? And so that's how we calculate cell potential. We first have to identify what oxidized and what reduced, and then we can write the half reactions according to that, and then we looked up the cell potentials, change the sign of the one that oxidizes, and then add them together. Alright, so another way we can describe these cells is by using what are called line notation. Right? You don't want to have to draw a picture of a cell every time. Okay, so instead we have what's called line notation, which is representative of the cell structure. Okay, so the anode components are listed on the left side, and the cathode components are listed on the right side. Okay, phase differences are separated by a single line, and that's like solid versus aqueous. Right? It could also be gas. All right. So the two sides are represented by separated by a double line, which represents the salt bridge. It's a double line. Okay. So the problem above, since magnesium oxidized, it would be the anode, right? And so magnesium is listed on the left. So we have our magnesium solid. We have a single line, our magnesium plus 2, 8 in our aqueous solution. Then we have our salt bridge, the double line. And then we have our aluminum ions in our aqueous solution. And then we have our single line to separate our aluminum solid from that. Now, if all of the components are ions, then none of the dissolved ions can act as the electrode, and so we have to use an inert electrode. And the inert electrode we typically use is platinum, PT. Right? So if you come across a problem where you have only ions, then the electrode, the solid piece that you would include in your reaction, in your cell diagram would be platinum. Right? It would not be part of the actual reaction, though, because it's inert, it doesn't react. So we want to describe this galvanic cell for the following half reaction. So if we have silver and iron, right? We want to first find out the balanced cell reaction and then answer the following questions. Okay, so in here, okay. So what first we want to know is what's going to oxidize and what's going to reduce, and we can determine that based on looking up the cell potential values from our chart. So we look on page 843, and we look up our potential for silver. We find that is 1.99. And then we look up the iron plus 3 to iron plus 2. You have to make sure you find the right one so that you're using the right information. Okay? And that's a 0.77 volts. Alright, so knowing that, we have to now determine what's going to oxidize and what's going to reduce. Remember, for our galvanic cells, our cell potential has to be greater than 0, so it has to be a positive answer. So the one that is going to oxidize, in order for the cell potential to be positive, right, when we change the sign, it still has to maintain a positive answer. So since this value here is smaller, right, if I make it negative, I will still end up with a positive answer. So this one's going to oxidize, and this one's going to reduce. Okay? So we'll flip this one over to show an oxidation reaction. And then we will change the sign to negative 0.77 volts. And then we will write the other half reaction. And its cell potential does not change because we did not flip it. And it's still reducing. Okay? So, now let's answer these questions. Does the silver receive or lose the electrons? Right? So silver, right, electron is a reactant, right? So it is receiving electrons, which means the iron is losing them. Again, that's because this is the oxidation and this is the reduction. Okay? Electrons flow in the cell always from anode to cathode. Right? Always from anode to cathode. And since iron is the oxidation, the iron is on the anode side, and then the silver is on the cathode side. Okay. So what compartment does the oxidation occur in? We just discussed that, anode. And the function as the anode, or the this is the left side, sorry, on the left, and that's the anode. Right, and then which compartment does the reduction occur in? That's on the right-hand side, right, and that is what we call the cathode. Okay. So, what would be the electrode for the silver positive one compartment? Right. So, since silver has a solid state, it would be the silver that is the solid state. And number 8, we have an electrode. What would be our electrode for our iron? Since neither of those has a solid state, they're both in ion form, we would have to use platinum. Okay? So now let's write our line notation. So left-hand side is our oxidation, or anode. Right? So we're going to start with our anode. Our solid for that is going to be platinum, we just said. That's our iron. We have a single line. And then we would have our ions, which we would list together, since they are both aqueous and they get separated by a comma. And then we have our salt bridge. And then we would have our silver ions. And then we'd have a single line. And then we'd have our silver solid. Now, technically, for all of our ions, we should write in that they are aqueous. Right? And again, these two are separated by a comma because they are the same state, so not a single line. So remember, the single line represents a change in state of matter. Okay? So in class, we're going to be practicing this some more.